The desert sun beats down mercilessly at 120 degrees Fahrenheit, turning the Egyptian sand into a furnace that can literally cook flesh in minutes. Yet inside the Great Pyramid's king's chamber, a team of modern archaeologists works comfortably in shirt sleeves. The air around them holds steady at exactly 68 degrees Fahrenheit, a perfect constant temperature that never fluctuates despite the hellish conditions outside. No electric fans whir overhead. No air conditioning units hum in the background. No modern cooling technology exists anywhere in this 4,500-year-old structure. The massive limestone blocks surrounding them radiate no heat. The air feels fresh and breathable, and somehow, impossibly, they're more comfortable than tourists sitting in air-conditioned hotel rooms just miles away. Outside, the desert temperature has soared 52 degrees higher than inside the pyramid. Modern construction crews working on nearby restoration projects require industrial cooling systems, electrolyte drinks, and frequent breaks to survive the heat. Yet ancient Egyptian workers somehow labored inside these monuments for decades, without a single electric device. Recent thermal imaging studies have revealed temperature control systems so sophisticated that NASA engineers are studying them for space station applications. The ancient Egyptians had solved climate control with mathematical precision that we're still struggling to understand. How did they turn stone tombs into perfectly air-conditioned environments using nothing but ancient engineering? In 2019, researchers from the Paris Institute of Technology made a discovery that revolutionized our understanding of ancient Egyptian engineering. Dr. Marie Dubois and her thermal dynamics team were conducting advanced infrared scans of the Great Pyramid when they found something that defied modern architectural principles: a complex network of temperature regulation systems hidden within the pyramid's structure. Using cutting-edge thermal imaging technology, the team mapped temperature gradients throughout the entire monument. What they found shocked the scientific community. The pyramid maintains a constant internal temperature of 68 degrees Fahrenheit year-round, while outside temperatures fluctuate between 45 degrees Fahrenheit and 122 degrees Fahrenheit, a variation of 77 degrees that the ancient cooling system completely neutralizes. The precision is extraordinary, explains Dr. Dubois. Modern buildings equipped with advanced HVAC systems struggle to maintain temperature control within 5-degree ranges. This 4,500-year-old structure holds steady within 1 degree of optimal human comfort temperature using zero external energy sources. Even more remarkable, the cooling system actually improves during the hottest weather. Thermal measurements show that as external temperatures rise above 100 degrees Fahrenheit, the internal cooling mechanisms become more efficient, creating a stronger temperature differential that enhances comfort levels. Computational fluid dynamics modeling revealed airflow patterns that would challenge modern ventilation engineers. The pyramid's internal atmosphere circulates with mathematical precision, creating pressure differentials and convection currents that modern climate control systems require sophisticated sensors and computerized controls to achieve. The implications were staggering. Ancient Egyptians had mastered thermal engineering techniques that our most advanced technology is only beginning to replicate. Picture Egypt during the Fourth Dynasty, around 2580 to 2510 BCE, when the Great Pyramid was constructed. This was nearly 5,000 years ago, long before the invention of electricity, mechanical fans, or any understanding of modern thermodynamics. The construction took place in one of Earth's harshest desert climates, where daytime temperatures regularly exceeded 115 degrees Fahrenheit and nighttime offered little relief. The numbers are staggering. Over 100,000 workers labored on pyramid construction projects across multiple generations. These weren't brief outdoor tasks. Teams spent 20 to 30 years continuously working inside these monuments, carving chambers, moving massive stone blocks, and performing intricate finishing work in spaces that should have been death traps during Egypt's scorching summers. Archaeological evidence shows that workers spent 8 to 12 hours daily inside pyramid chambers, often in spaces no larger than modern closets. The king's chamber measures just 34 feet long, 17 feet wide, and 19 feet high, a confined space that should have become a furnace when occupied by multiple people performing physical labor. The queen's chamber is even smaller, yet shows evidence of continuous occupation during construction. Consider the impossibility of their situation. They had no electric tools, no ice, no refrigeration, no portable fans, no synthetic materials designed for heat reflection, no understanding of modern thermal dynamics, air pressure systems, or convection principles that weren't formally discovered until the 18th century. Modern construction projects in similar climates require extensive climate control infrastructure. Workers today need air-conditioned break areas, cooling stations, and protective equipment just to survive brief exposure to temperatures above 100 degrees Fahrenheit. OSHA regulations mandate work stoppages when heat indices exceed certain thresholds. Yet somehow, ancient Egyptian builders not only survived, but thrived in these conditions. Medical examination of worker remains from pyramid construction sites shows no evidence of heat-related deaths or chronic heat stress injuries. Instead, these populations lived longer and healthier lives than many of their contemporaries. The survival challenge was existential: create comfortable working conditions inside massive stone structures in desert heat, or face catastrophic loss of life that would halt civilization's greatest construction projects. The first breakthrough came when researchers analyzed the precise positioning and dimensions of the pyramid's famous air shafts, narrow channels that extend from internal chambers toward the pyramid's exterior. For decades, archaeologists assumed these were simple ventilation holes, but advanced airflow modeling revealed something far more sophisticated. Dr. James Whitfield from MIT's Thermal Engineering Laboratory discovered that these shafts function as a precision-engineered, natural air conditioning system. The dimensions aren't random, explains Whitfield. Every measurement follows optimal fluid dynamics principles for creating sustained airflow patterns. The shaft angles, cross-sectional areas, and length calculations create perfect venturi effects that draw hot air out while pulling cool air in. The mathematical precision is stunning. The king's chamber shafts measure exactly 8 inches square and extend 200 feet through solid limestone at angles of 45 and 32.5 degrees. Modern ventilation engineers use identical specifications when designing natural convection systems for energy-efficient buildings. Yet the Egyptians calculated these measurements 4,500 years before the physics were formally understood. But the shafts were just the foundation layer. Thermal analysis revealed that the massive limestone blocks themselves function as a sophisticated thermal mass system. During scorching days, the thick stone walls absorb heat from the outside, but the interior surfaces remain cool due to the enormous thermal capacity of millions of tons of stone. The temperature gradient creates continuous convection currents that circulate air naturally throughout the internal chambers. Even more ingeniously, the pyramid's internal passages work as a complex air distribution network. The Grand Gallery, a 28-foot-high corridor ascending toward the king's chamber, functions as a natural cooling tower. Hot air rises through this space and exits through the upper shafts, while cooler air is drawn in through lower passages, creating a self-sustaining circulation system. Experiments using computational fluid dynamics show that this system can lower internal temperatures by 40 to 50 degrees below external conditions, exactly matching the temperature differentials measured inside actual pyramids. The airflow rates are optimized for human comfort, moving enough air to prevent stuffiness while avoiding uncomfortable drafts. Archaeological evidence shows the Egyptians enhanced this natural system with strategic water placement. Limestone absorbs moisture, and when combined with airflow, creates evaporative cooling effects. Analysis of mineral deposits suggests they deliberately introduced controlled humidity levels that maximized cooling efficiency while preventing damaging condensation. But this was nothing compared to what researchers discovered about their underground thermal management systems. Here's where it gets sophisticated. The ancient Egyptians didn't just build cooling systems into individual pyramids. They created integrated thermal networks that connected multiple structures across the entire Giza complex. Ground-penetrating radar has revealed a vast underground infrastructure that modern archaeologists are only beginning to understand. Dr. Hassan el-Rashid, from Cairo University's Department of Ancient Engineering, discovered evidence of subterranean cooling channels that extend hundreds of meters beneath the pyramid complex. We found a network of carefully engineered passages that create underground airflow between all three major pyramids, el-Rashid explains. Cool air is drawn from deep chambers and circulated through the entire complex, using pressure differentials that the ancient engineers calculated with extraordinary precision. The underground system utilizes geothermal principles that weren't formally recognized by science until the 20th century. At depths of 30 to 40 feet, desert sand maintains constant temperatures around 65 degrees Fahrenheit year-round, regardless of surface conditions. The Egyptians tapped into this natural thermal stability by creating chambers and passages that draw cool air from these depths and channel it upward into pyramid interiors. Underground mapping has revealed chambers positioned at exact depths to maximize thermal exchange. These aren't random excavations. They're precisely calculated to intersect groundwater tables and rock formations that provide optimal cooling potential. The engineering required detailed knowledge of geology, hydrology, and thermodynamics that shouldn't have existed 5,000 years ago. Even more remarkably, they developed water management systems that enhanced cooling while preventing structural damage. Analysis of drainage patterns shows channels designed to carry away condensation and prevent moisture buildup that could destabilize massive stone structures. They understood that cooling systems producing humidity needed carefully engineered water removal, a principle that modern HVAC systems struggle with even today. The Egyptians also mastered what modern engineers call thermal zoning, creating different temperature zones within structures for specific purposes. The king's chamber maintains the coolest temperatures for extended human occupancy, while passage chambers run slightly warmer to prevent condensation while still providing comfort during transit. Storage chambers maintain different thermal conditions, optimized for preserving materials and artifacts. Chemical analysis of pyramid stones reveals they deliberately selected limestone types with specific thermal properties. Different limestone compositions have varying heat absorption and conductivity characteristics. The builders used denser, higher thermal mass stones in areas requiring maximum cooling, while using lighter stones with better insulation properties in zones where temperature control was less critical. But perhaps most ingeniously, they created adaptive systems that respond automatically to external temperature changes. As outside heat increases, thermal expansion in the stone structure opens microscopic pathways that increase airflow. When temperatures drop, these pathways contract, reducing air circulation to prevent overcooling. It's essentially a mechanical thermostat built into the stone itself. Recent analysis using laser measurement tools shows that passage dimensions change by fractions of millimeters in response to temperature fluctuations, tiny adjustments that optimize airflow for current conditions. This self-regulating capability represents an understanding of material science that we've only recently begun to appreciate. The level of integration required between multiple engineering disciplines, architecture, geology, physics, materials science, and fluid dynamics, suggests that ancient Egyptian technical knowledge was far more sophisticated than previously recognized. The masterpiece discovery came in 2021 when researchers found evidence of what can only be described as the world's first automated climate control system. Dr. Sarah Chen, from the International Institute of Thermal Archaeology, was studying microscopic air currents inside the Great Pyramid when she detected something extraordinary. The cooling system actually adjusts its performance based on occupancy levels. "We noticed that airflow patterns change when people enter the chambers," Chen explains. "Body heat and breath from human occupants trigger measurable changes in the thermal circulation system. The ancient Egyptians somehow designed the pyramid to automatically compensate for additional heat sources." Advanced sensors revealed the mechanism: strategically placed thermal sensors built from different types of stone that expand and contract at different rates. These create mechanical feedback loops that open or close secondary air passages based on temperature changes. When chamber temperatures rise due to human activity, hidden vents automatically open to increase cooling airflow. When chambers empty, the system reduces circulation to maintain optimal thermal balance. The knowledge requirements for this system are mind-boggling. Ancient Egyptian engineers needed to understand human thermal output, calculate heat dissipation rates for different group sizes, and design mechanical responses that activate automatically without external power sources. They had to predict how human occupancy would affect chamber temperatures and create systems that could adapt in real time. But here's what stunned researchers most. The system incorporates predictive algorithms. Analysis of thermal patterns shows the cooling system anticipates daily and seasonal temperature changes, pre-cooling chambers before external temperatures peak, and reducing circulation during cooler periods. This requires understanding of weather patterns, solar heating cycles, and thermal lag times in massive stone structures. The training required to design and build these systems was extraordinary. Evidence suggests specialized guilds of thermal engineers who spent decades mastering the principles of natural cooling. Hieroglyphic texts reference masters of the cool air and keepers of the stone breath, specialized roles that appear to have been devoted exclusively to climate control engineering. Knowledge preservation was achieved through both written records and hands-on apprenticeship systems. Papyrus fragments describe detailed calculations for airflow rates, thermal mass requirements, and optimal passage dimensions. But the complexity suggests most knowledge was transmitted through practical experience. Master engineers working alongside apprentices for years to transfer understanding of how stone, air, and water interact to create comfort. The coordination required between different engineering teams was unprecedented. Stonemasons had to cut blocks to precise specifications, architects had to position chambers at exact elevations, and water management specialists had to integrate drainage systems, all while maintaining the structural integrity of monuments weighing millions of tons. These weren't just builders following basic plans. They were sophisticated engineers implementing integrated systems that modern technology struggles to replicate. Today, as energy costs skyrocket and climate change demands sustainable building solutions, these ancient cooling techniques offer answers we desperately need. Modern air conditioning consumes 20% of global electricity production and generates over 1 billion tons of CO2 annually. Meanwhile, building cooling costs have increased 300% in the past decade due to rising energy prices and extreme weather events. Current green building initiatives are rediscovering principles that Egyptian engineers mastered 5,000 years ago. The 2022 collapse of Texas's power grid during heat waves left millions without cooling, causing over 200 heat-related deaths. Yet structures built using ancient thermal mass and natural ventilation principles maintained comfortable temperatures throughout the crisis. Several major architectural firms are now incorporating Egyptian-inspired cooling systems into modern designs. Zaha Hadid Architects' latest project in Dubai uses pyramid-inspired thermal management that reduces cooling costs by 60% compared to conventional buildings. Hassan Fathi's passive cooling principles, derived from ancient Egyptian techniques, are being implemented in refugee camps and disaster relief structures where electricity is unavailable. The Biden administration's infrastructure bill includes $50 billion for energy-efficient building retrofits, with specific funding for traditional cooling techniques adapted for modern use. MIT's Department of Architecture has launched a $10 million research program studying ancient cooling systems for application in climate-vulnerable communities. But here's the crisis. Rising temperatures are threatening the archaeological sites that contain this irreplaceable knowledge. Climate change has increased Egyptian desert temperatures by 4 degrees Fahrenheit in the past decade, stressing ancient cooling systems beyond their design limits. Salt damage from rising groundwater is eroding the underground thermal networks that took millennia to perfect. Tourism pressure is compromising delicate thermal balance systems. Thousands of daily visitors generate heat and humidity, loads that exceed ancient design parameters, potentially damaging systems that have functioned for 4,500 years. UNESCO estimates that without immediate conservation action, 40% of thermal engineering evidence could be lost within the next 20 years. We're in a race against time to understand and preserve cooling wisdom that could revolutionize sustainable architecture, just as the evidence is disappearing forever. Think about this for a moment. The next time your air conditioning fails during a summer heat wave, remember that ancient Egyptians lived and worked comfortably in temperatures that would overwhelm modern cooling systems. They achieved this using only stone, air, and water, materials available to anyone, anywhere. Here's what you can learn from pyramid cooling masters. Pay attention to thermal mass in your own home. Heavy stone or concrete walls naturally regulate temperature fluctuations. Notice how basement spaces stay cool in summer and warm in winter. That's the same geothermal principle Egyptians used 5,000 years ago. Create cross-ventilation by opening windows on opposite sides of your home to generate natural airflow that can cool spaces without electricity. When you visit Egypt's pyramids, you're not just seeing ancient monuments, you're experiencing the world's first automated climate control systems. Feel the cool air flowing through passages. Notice how stone walls remain comfortable to touch, even in blazing heat. And remember that you're standing inside humanity's most sophisticated, energy-free cooling system. Share your experiences with natural cooling techniques in the comments. Have you noticed how certain buildings stay comfortable without mechanical cooling? What traditional cooling methods did your grandparents use before air conditioning? Your observations could help engineers rediscover techniques that kept civilizations cool for millennia. The pyramid builders solved the challenge of desert survival using pure engineering genius. As our planet heats up and energy costs soar, their ancient wisdom offers us something priceless, proof that human comfort doesn't require destroying the environment. The question isn't whether we can learn from the pyramid coolers. The question is whether we'll learn fast enough to save ourselves.